So hi everyone, I'm Vasudha, and today I'll be talking about my work SyntStereo2Real. It's an edge-aware GAN for translating synthetic remote sensing images to look more realistic, and these synthetic images are later used for training stereo matching networks. It was done as a part of my master thesis work, and my co-authors are Mario Fuentes Reyes, Dani Pananijan, and Xenia Bitna. They were my supervisors, and they work with the German Aerospace Center. So, yeah, AI has been used extensively in a lot of applications, from medical, healthcare, to finance, to tracking carbon emissions and vegetation monitoring and whatnot. The application in which we are focusing is to use it for urban planning, particularly generating 3D models of the cities, from which we can use it for various other purposes. So in order to create 3D models, we need the depth values or the height of the buildings. And to obtain the depth values, there are multiple ways to reconstruct 3D models. One is from images, and one of the method is from stereo matched images. So what is stereo matching? So what is stereo matching? Basically, you have a surface and there are multiple points, and you take images from the top, such as aerial view or satellite view, and you try to locate a particular point from two views. That is, two cameras take images of the same point in different views, and you try to find the matching points in the left and right images. And once you find the matching points, you calculate how much the point has moved, and that is the disparity. So with the help of disparity, we can calculate depth. There is an inverse relation between the depth and disparity, which is given here. So here, Z is the depth, and F is the focal length of the camera which we use, which we know, we set it as a parameter. B is the baseline. Baseline is the distance between the cameras, which takes images from two different views. And disparity is the shift in point from left to right image. So if we have the disparity, we can calculate the depth or the depth of the height of buildings, and then we can calculate the 3D models. So stereo matching is the process of estimating the disparity between 2 points, between two images. And so why it is important is we know we need the 3D model. And it is actually very difficult in case of remote sensing to obtain stereo matched images. Most of the images we get are from satellite. And in terms of satellite images, they take it once in 2-3 days. And obtaining matching points between the left and right images can be difficult because there can be change in the building position, there can be change in lighting, there can be trees cut, and it is extremely difficult to find the matching position in the images taken from satellites. Another option would be is to use aerial cameras or which is used to capture from a lower height, but it's really expensive and also cumbersome to take images. Also, you can see the ground truth disparate map, which is here on the right, is not really complete and not very accurate, which we can use for training machine learning models. So when we try to train with this approximate disparity maps, there's a lot of hallucination. So we need more data, obviously, for training deep learning models. And so the other option is to use synthetic data sets. Synthetic data sets are nothing but images or data sets which are created from a simulation which is very close to the real world characteristics. So, and since we create the synthetic data set, we have access to entire ground truth information from labels to disparity maps to segmentation maps to instance IDs and everything. Some of the popular synthetic datasets are SceneFlow, Syntel, and SyntCities. SceneFlow was from University of Freiburg. They had 3 datasets. One was driving, optical flow, um, and Monka. All of them are used for training similar tasks such as optical flow or disparity networks. And Syntel, it's an open source movie. It's an open source dataset, but it's actually a movie which has lots of large objects moving in faster motion. So this was helpful to train optical flow networks again to for the object to detect fast moving objects. And since it's an open source dataset by people from DLR, uh, it is um, it is a simulation of urban areas. They use it for training stereo matching networks, and it consists of 8,100 pairs of left and right images. And these images resemble cities from Paris, Venice, and New York. So we have somewhat good amount of synthetic data sets that are available right now. But when we try to use these data sets to train the deep learning network, they suffer from the problem of domain gap. So the networks fail to adapt as well to the synthetic data sets as the real images. So we need to reduce this gap. And the community has also come up with a solution such as using domain adaptation networks. So what is domain adaptation? Basically, you try to make the synthetic data set or uh, follow the distribution of the images in synthetic data set very much close to the realistic data set. And there are, so the main or the core idea is that both synthetic and real data sets must have some domain agnostic features. That is, they both should represent the same base scenario. That is, you cannot have a synthetic urban image and try to map it to a horse image in the real domain. So they should have an same features which are described in both the domains, and certain domain specific features such as appearance, lighting can vary, and that would be learned by the network. Some of the popular domain adaptation networks are GAN-based networks. GAN networks are generator discriminator network. It's basically competitive learning. The task of the generator is to create realistic images of the kind of images you get, like of the target distribution. And the task of discriminator is to identify if the generated image is real or fake, which one is the real or fake. And there are numerous thousands of GAN-based networks available right now, but a lot of them are not applicable because we do not have a paired translation. What do I mean by paired is I do not have the mapping, that is, I do not have a synthetic image and I do not have the realistic version of the synthetic image. So I do not have the same image in both the domains. So it is not paired, it's an unpaired image translation problem. As you can imagine, if I had the realistic version of synthetic image, I would not end up in the current problem I am in, because it's very rare to find paired images of satellite images. But there are thousands of Google Map images which has the appearance and style of urban areas. So we use CycleGAN. It is one of the predecessors in unpaired image translation. We try to implement we try to use it for a task. The cycle GAN has 3 main losses: reconstruction loss, cycle consistency loss, and adversarial loss. The task of reconstruction loss ensures that the quality of generated images try to resemble as much as possible to the input. And cycle consistency loss makes sure that the translation um, does not cause new hallucinations or does not create new items and new elements in the image. And adversarial loss is for training between the generator and discriminator. I would just look at the question. Yes, I can describe. I don't know. I can say what is the AV driving synthetic data set shared in the previous slide. I'm sorry. Is it this one? Which one are you asking? I didn't understand.
Yeah, Haresh's question was during the synthetic data slide.
This one. This is from driving dataset from SceneFlow. Okay, and this is Syntel, and this is SyntCities. The next one is slide of. Okay. It's for the same person. Can you describe the problem you're trying to solve? Yeah. So the problem is we have very few real images which are stereo matched. I explain what stereo matching. That is basically a pair of left and right images representing the same point. And with these stereo images, you can make a 3D model. And we do not have we do not have enough pairs of such images of urban areas at least, or remote sensing areas. And we are trying to fill that gap by using synthetic data sets, and not just synthetic data sets, but trying to create more realistic synthetic data sets with the use of GAN. I hope it's clear. Okay. 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 So yeah. Okay, sorry. So this is how CycleGAN does, and yeah. So the problem with CycleGAN was in remote sensing domain. Again, it has way too many features. It is feature rich. There are lots of trees, lots of buildings, roads, greenery, different lighting, shadows. So the model hallucinated badly because it did not know where to put the elements, and it generated a lot of new elements in the generated images. These are some of the translated images here. And yeah, so we also tried CUT. It's a contrastive unpaired translation. It was proposed by the same authors of CycleGAN. It's a one-way image translation. And yeah, so yeah, the problem is the target data set and the target and the original data set are unbalanced. What I mean is that the real satellite images has a lot of features which are not represented completely in the synthetic images. They are very clean. And using these contrastive laws, the model tries to hallucinate a lot. And with hallucination, it is impossible to try to find a matching point in the left and right images because they should be similar. So it was not an option to use one of these networks. So one of the existing work which addresses this problem is StereoGAN. It was a paper in CVPR in 2019. So they do exactly the same. They try for unpaired image translation while maintaining stereo constraints, and it is very straightforward. So they first do unpaired image translation using CycleGAN, and then with the translated images, they do stereo matching with another network, DiskNet, and then try to optimize it together by training them together. Yeah, so this is one of the networks, but it was too heavy because you're jointly optimizing two networks to achieve a single task. So we were looking for other options which could be possible. CecoGAN. CecoGAN is one network which actually worked pretty well because while performing image translation, there was not a lot of hallucination. And this is quite important because, again, as I said, it is important to find the matching points. So it is based on content style disentanglement, or yeah. So they have a autoencoder based structure, and the main concept between the main concept in GAN is they have a shared encoder, and the shared encoder tries to find uh, similar content code both in the real domain and the target domain. And in this way, it tries to find the matching elements in both the domains. So this one worked pretty well. So we thought of using this network and applying stereo matching to this to yeah, for our task. There's a question. Create synthesized data system. Yes, yeah, exactly. So these are not just used for disparity. We can also use it for segmentation, and we tried it for segmentation alone of rooftop data sets, and we didn't try it for any other task. But yeah, not just for disparity, but also for building segmentations. Yeah. Okay. So the main model architecture is we give the input. Input is the left, right, and disparity map of the synthetic domain, and a real image from the real domain, and two style codes. These style codes are from, these style codes are statically initialized, and these are not trained. These are basic. There's another question. Is the goal to create Is the goal to create pair of images for training for depth estimation? Yeah, the goal is for calculating the depth, but calculating depth is a straightforward formula. If you have the disparity, you can calculate the depth. It's inversely related, which I showed in slide 2. Is it possible to use one real image and generate image from the second sensor? What sensor do you mean? What is the sensor? I didn't understand. So okay, I'm explaining the yeah. Let me explain. So there are left, right, and disparity maps, and XB is XL, XR, and XT are the images and the disparity maps in synthetic domain, and XB is the image in the real domain. SA and SB are the style codes. Why we have predefined the style codes is the task of the encoder is to separate the content code and then combine it with the style code later to generate for the discriminator to identify if it's real or fake. So that's why we give pre-initialize the style code. And this is done by randomly initializing with a normal distribution. And then we pass it through the Sobel operator. Let me tell you why we use a Sobel operator to obtain the edge maps of these images, and why we need edge maps. As I told, it is very important to obtain matching to calculate disparity. And it is how do you find matching is in terms of edges or corners, and these edges help to easily identify matching points instead of just plain textures. So we thought it is important to specify or additionally incorporate the edge information along with the images. And you can obtain this from the Sobel filter, and these are just it's a pretty standard network. And then you also get the edge map of the real domain, and then you have the two style codes from the input. So this is passed to the encoder, and the encoder performs content style disentanglement, which I will explain more in detail in the next slide. But yeah, it performs content style disentanglement and it generates particular output. And then based on the generated output, the discriminator tries to discriminate if it's real or fake. And then various laws, such as the reconstruction loss, cycle loss, and adversarial loss. All these losses are carried out, and then it causes a GAN training. There is like a generator discriminator training. So along with these three losses, we also use the warping loss to enforce the disparity constraint. So what is a warping loss? It's basically you take the left image, add the disparity values to it, and you see if the right image is generated from it. So it is just warping the left with the disparity to see if the right image has been generated. So we perform warping on the generated images from the generator and then calculate loss from it. It's a combination of L2 and SSI loss. I will explain later. But yeah, so additional to the standard GAN losses, we also incorporate a warping loss to make sure that the stereo consistency is maintained. So there are some questions. Oh, sorry. Why you are doing synthetic data? Sorry, my previous question was confusing. I missed the reason why you are doing synthetic data. Yeah, we do not have a lot of real images. We do not have a lot of image pairs, so we use synthetic data. How do you get style code from source? Yeah, we do not get style code from source or target domains. We use a standard style code. It's just a one-dimensional vector, which is initialized based on normal distribution. So yeah, I just brushed through so I will elaborate what is there in this encoder part or the generator part here. So, and how the edge is getting distributed. So here you can see, you get the images, source RGB images of the source and target domain, and the edge maps of the source and target domain. These are all passed to the encoder. And the task of the encoder is to generate content codes or latent maps. So these are here you can see the content codes are of the RGB images. Similarly, you get the content code of the edges. You call them as edge code, and I just like add them, concatenate the edge code to the content code, and make sure that at least these portions should not be altered during the image translation. So instead of just passing the images, adding both the content with the edge code and then passing it to the decoder will make sure that the hallucination is quite less. And these style codes are the pre-initialized ones. They are combined with like multiple A and A, that is like source domain, target domain, and all the it is combined with different style codes to generate different outputs. And based on these outputs, various losses are calculated as by the discriminator with adversarial training, and also cycle consistency and reconstruction losses are calculated. So this is the architecture of the generator. And here we show how like the edge maps are incorporated along with the encoder and decoder. Just a second. How much data is created in synthesized dataset compared to what's in real dataset? Okay. So in real images, we had around not even like 800 pairs of images, and synthetic was around 8,100. So it was like 10 times more. So the generator follows an autoencoder architecture, and this is based on MUnit. In MUnit, they have same content style disentanglement, but they also train the style part to they also have multiple style codes which are again trained in the network. Here we just use a standard style code. And then there are two discriminators, each one for each domain, and they follow a patch GAN based architecture. It is trained for 100 epochs, patch size 4, and Adam optimizer. Yeah, these are the various loss functions. These are pretty standard loss functions: reconstruction loss, cycle loss, and the adversarial loss, along with the warping loss, which I mentioned. So warping loss, we use L1 and L2 losses for reconstruction. We use L2 loss for reconstruction and adversarial loss, and for cycle it's an L1. And for warping, it's a combination of L1 and SSIM loss. So L1 is standard mean without the square part, and L2 is the squared mean difference. And SSIM loss is the structural similarity index metric, and it calculates the loss between how well the structure is maintained in both the images. And we calculate this loss from the right translated image uh, and warp the left image with the ground truth disparity, and then compare both these images. These are the hyperparameters which we use for training, and beta 1, beta 2 are the Adam coefficients. So yeah, data sets. For realistic dataset, we used US3D dataset by Data Fusion Contest. It's open source dataset, and mainly they encourage for stereo matching networks or urban datasets. Now they have for rooftop classification segmentation tasks also. The other one is the synthetic dataset is SyntCities. Yeah, as I explained, it has images resembling cities, Paris, Venice, and New York, because Paris and Venice have like relatively shorter buildings. New York has tall buildings with a lot of shadow effects. And one problem was a lot of these images had so much greenery in it, and which was not relevant in the synthetic images. So we filtered out images which had at least 15% of it as buildings to make sure that the image translation is consistent. Yeah. Also, not just on remote sensing domain, but also in other domain, we wanted to check if the network is performing well. So the other one was in autonomous driving. We use Kitty 2015 dataset as real domain, and driving from CFLU as synthetic dataset, and tried image translation with disparity. So all the network is evaluated based on 3 metrics. We did both a qualitative and a quantitative evaluation. In quantitative, it's based on 3 metrics: image, how well the image is translated, and based on the disparity estimation, how accurate the disparity maps are. And third one is like how efficient the network is, like how fast the network can train, and it should not be really bulky. So image translation is based on FID. It's a pretty standard metric. And disparity map is based on MAD, which is just the absolute difference between 2 pixels, and take a median of it. And this is 3 pixel accuracy, that is accuracy difference between the, take the difference between 2 pixels, and if its difference is more than 3 pixels, then you calculate it in the 3 pixel. Similarly in 1 pixel. And yeah, number of learnable parameters. So yeah, FID, we compare it with stereo GAN because that was the only other network which was performing the exact task. So image translation from stereo GAN was okay, not so good, but the FID, lowered FID, it's better, it looks more realistic. So yeah, the network performed well in terms of image translation, both for remote sensing datasets as well as autonomous driving datasets. And in terms of number of learnable parameters, the stereo GAN had 2 networks. One was cycle GAN and DispNet, and tried to optimize it together. So it had 54 million parameters, but I think SyntStereo2Real is just an image translation network with an additional loss as a disparity constraint. So it has only 11 million parameters, or trainable parameters. Yeah, and the disparity estimation also, the MAD has significantly reduced with our network, and the accuracy has also increased from the baseline for both the data sets. These are the qualitative, or you can see the image translation results. StereoGAN tried to translate a lot of shadow areas into green patches or sceneries in our network. It has tried to prevent that, at least to some extent. And yeah, the translation also looks like more realistic. At least in case of disparity, it looks much better. This is for driving images. And these are the disparity estimation maps. Yeah, in case you want to see these images, these will later be available, and you can see it. It's also in our paper online in archive. So yeah, the disparity estimation maps are more complete because of the use of edge maps, and it helps us to retain the structure. This is for driving to Kitty. Again, disparity maps are much more complete. We also performed ablation studies. Our main contribution was to include edge and also use a warping loss while training the GANs. So we tried with all the three parameters, like all the two parameters with and without it. And although individually addition of edge or addition of disparity map does not significantly reduce the MAD or increase the accuracy, but when we combine both of these methods, there is like a significant improvement in accuracy. That was one of the very interesting findings. Yeah. So here we provide. Did you notice any loss of this? There was no missing foreground, or we did not have missing. We had the opposite, where we had more hallucinations, or it generated some kind of textures for driving and kitty. So I will show you the. So yeah, so here you could see the background, it kind of generated some hallucination or some artifacts, but this was only for driving to Kitty. It did not do it in this. And we also spoke to other authors, and they mentioned they had similar problem when working with driving to Kitty. But I don't really have an exact reason. One thing what I thought was since it does not have any sharp edges, or it's just texture based, there's a lot more scope for the network to hallucinate, and I don't really have the network doesn't have exact content to translate to, but I don't know if that's the exact reason. Yeah, I hope it helps. I don't know. Yeah, so it provides, so this network provides a framework for unpaired translation for both left and right images, or in that case, we can also have way more images. It performs a content style disentanglement, which is similar to MUnit, and we incorporate edges to the model while translating, also incorporate warping loss as a constraint instead of addition of an entire network, such as Dispnet. It can be really heavy, and we can avoid that. And this can be also extended to other downstream tasks, segmentation, classification, which is really important right now. And yeah, it was fun.